Okay, everybody, could you see my screen? Hello, everybody, can you
Yeah,
see my?
we can see it.
Okay, great. Yeah. Um, Here you see there are a couple of numerical problem. So today mainly you please make practice. So everybody please take your pen, paper and calculator and make practice. The problems are about permanent magnet DC motor and that universal motor mainly. Um, Everybody, you can open the class notes, previous two class notes and or any class notes and see the required equation and please solve these problems. And you see, I have write down the answers for you so that you can understand that you did it correctly. So please everybody start and make practice. So therefore, you see, last class we discussed, I think, 3-4 numerical problems about permanent magnet motor, universal motor. So based on that, you will look those things. Already those were uploaded on eCourseware and look and see and what equation you can use here and then match that you are getting the correct result. So this will be very good practice for you for the problems. And then this will help you a lot for the upcoming midterm exam third, I think to be held on November 11th, most probably. So the first one is like a two-pole permanent magnet DC motor is running at 1250 RPM and has an armature resistance of 1.5 ohm, a constant field flux of 0.18 webers, a total number of armature conductors of 60, and a number of parallel paths of 2. If the applied voltage to the motor is 240 volt, then calculate the value of armature current of the motor. So based on that, how you can calculate the armature current I. So you see, and then answer should be 10 ampere. So please everybody open your note, and I think the previous two classes will be fine, at least the last class. So everybody please take your time, feel relaxed and open the notes and see the equation and understand these and then solve, make practice. Let me bigger, much more bigger. Yeah, I think now it is much more clear to you. I mean, although these problems are very similar to what we discussed in last class or previous class, but still you need to look carefully. First, you need to understand those problems and then start these things. So whenever you have any questions, please ask me. Don't hesitate to ask me for any clarification or anything. Uh, But everybody, please try your best. It's a very good practice for you. So therefore, as a hands for the first one, because you are asked to calculate the value of armature current, at first write down the equation for armature current. And then you can see what is given, what is not given. So the first step should be write down the correct equation for that armature current. What is the armature current equation? And then you see what is given, what is not given, and how you can get that. Sometimes you might need to use the even previous equation, not just permanent magnet or universal motor, DC generator equation, DC motor equation, all things will be involved. Uh, so first write down the armature current equation and then you see how you can get the values. So are you all trying?
Yes, sir.
Yeah.
Yes, I have a number one done now.
Yeah, I finished the first one. I'm working on the second one.
Okay, so you got the 10 ampere, right?
Yes, 10 amperes.
Okay.
Yep, sure did. 10 amps.
Okay, that's great.
Okay. Hey, Dr. Ali, last class we did I just want to make sure I understand. We had
Okay, go ahead.
E equals the flux times times speed over speed. We did times lowercase p over a. Could you remind me what a was for in that equation?
So say the equation once again. E equal to what you said? Equal to K.
Yeah, it was the flux times the number of conductors times the speed over 60, and then we multiplied that times lowercase p for the pole number over a, and I just can't remember what the a was equal to.
It's parallel
Oh,
paths.
A was for parallel paths. A was for parallel paths. So are you talking about the number one right now?
No. For number 3 from yesterday or last class, but
Sorry, number 3. Yeah, okay.
from last time, 3 from last time.
Oh, 3 from last time. Okay.
But-
So, okay.
I think I've got it. Thank you.
Yeah. So therefore, I think there it was the armature constant, right? In the problem 3 of the last class. Armature constant, and then there was torque constant, right? So
Okay.
yeah, so for the armature constant will be G, capital Z over 60 multiplied by phi over A. That is your actually K, armature constant. And then if you multiply by the flux phi, then that will be your torque constant
Okay.
in case of permanent magnet motor, because permanent magnet motor flux is constant. So that's why you have to multiply flux with that armature constant, which is G over 60 multiplied by phi over A.
Okay. So Z Z is the number of conductors. Capital A is the parallel paths.
Right. And phi
Okay.
is
All right.
the
Thank you.
yeah, and phi is the full number. Yeah.
I just got the same answer for number 2, by the way.
Oh, the 6.1 for Newton meter.
Yeah.
Oh, okay, great. Yeah, okay. So everybody is done number 1, or are you struggling still?
Yes, I've done number 1. I'm almost finished with number 2 now.
Okay, great. Yeah. Everybody, please be relaxed and take your time, but then do properly. It's a very good practice. The goal is that sometimes, even though by reading the problem, you understand what to do, but then unless you take your pen and paper and calculator solve, so you're not sure that you understood correctly. That is the goal of this practice. That's why understand and then use your pen and paper and calculator and see that, okay, you're getting it.
I got the same answer for number 2.
Oh, okay, great.
I got the same answer as number 2.
For number 2?
Ye-
Okay, great. So does anybody have any questions for number 1 that is still you're doing, and do you have any questions, confusion? Number 1, everybody? I mean, just feel free to express your concern and then I can help.
Yes, sir. So did you start this one off by solving for E? And could you tell me what you got for that?
You're talking number 1?
Yes, sir.
Okay, so first, did you write the correct equation for armature current? Like IA is VT minus EV over RA. Did you write
Yes,
that?
sir.
Okay.
I did.
Yeah, okay, and then you can see VT is given. VT is 240 volt. Okay, and then RA is also given. See the beginning of the second line, RA value is 1.5 ohm. Okay.
Yep.
Now you need EV. So EV should be that equation, DC generator equation, phi Gn over 60 multiplied by phi over A.
Yep.
You see that we used on equation before, phi Gn over 60 multiplied by phi by A. That should be the back voltage equation. I mean, in case of motor, we call it the back voltage, but in case of generator, that is the same equation. We call it induced voltage. Is this fine?
Yes, sir. That's the equation I used. I think I just got confused, but I give me a few minutes and I'll check back with you. I think I've got it now.
Yeah, please go ahead. So make sure that your EB should be 225 volt, 225 volt EB. Make sure that you are getting that one. Otherwise, you will be getting incorrect result. Yes. So for everybody, please try your best. Yeah. So everybody, you must understand and then solve this.
Can I have a hint on how to do 3B? I wrote down the equation for power,
Okay.
but don't we need to know the new current to find the new torque? We have the torque constant from part A.
Yeah. So you need new back voltage and you need new armature current.
So
Both EB and armature current should be new.
yes.
Yeah.
But
then you need to use the same torque constant value from the previous
yeah.
one.
I guess I need to look back at my notes. I'm not sure how to find EB from what we have.
Yeah. So therefore, see, take time. I mean, see all the notes from the previous class and figure it out.
Oh, got it. Never mind.
Okay. Yeah.
Okay, Dr. Ali, I fixed my mistake in number 1 and I got that, and then I've also got number 2 finished.
Okay. Great. Yeah. So please, everybody, take time. Yeah. Please understand that is the goal of this today's this practice. Yeah. Therefore, again, for everybody, for number 2, as you can see, the question is calculate the developed torque of the motor. So therefore, the first step should be you write down the required equation for developed torque. So what is the torque? That power over omega, speed in radian per second, power over omega. And then you can get what you need to find out. The back voltage is given, back EMF is 110 volt. So the very first step should be you write down the equation for torque, that power over omega. Then what is power? Then back voltage multiplied by the armature current, that is the power. Then you see how to get those values and then plug in there in the torque equation. That's all. Hello, Jared, are you getting the results? Sir. David, are you trying?
Yes, sir.
Okay, please keep going. Just everybody feel free to, if you have questions, then ask me. Hello, JC. Moses, are you doing? Are you getting the results?
I had to fix my microphone. Yeah, I got number, and I've almost got number 2. Had to fix a mistake in number 1.
Okay, okay. Oh, so JC, you are talking, right? Yeah, yeah. Okay, got it. Yeah. Alajmi, are you trying?
Yes, I just came to the class. I will start working on it.
Oh, okay, okay. So Masa,
Yeah, I'm working on them.
oh, okay, okay, please. Nolan, are you working?
Yeah, I'm working through them.
Oh, okay, please, everybody. So anytime if you have then questions, then feel free to ask me. Patrick, are you getting?
Yes.
Okay, okay, please.
I'm in the.
Okay, it looks like some microphone issue. Okay. Jared, are you getting the results?
He had to step out for a minute.
Okay. It looks like he's not responding.
Could I ask for a hint on number 3? Are we solving for the current on the first part, or are we trying to solve for something on the first part and then use that to solve for the second part?
Yes, that's right. For the first part, you will be getting the torque constant. Then the torque constant will be the same for the second part. Now, for the second part, you should have the new back voltage and the new armature current for the second part. That's the thing. And now to calculate the back voltage, I'm talking about the second part. To calculate the back voltage, you need the torque constant. That torque constant will be the same that you will be calculating from question A, from previous part.
Okay, so last class for the example number one, we said that EB was equal to torque constant times flux times omega, and then we set that equal to, I believe, uh, was it K1 omega, and then we solved for the torque constant.
Yeah, exactly. So therefore,
What could you remind me what happens to the flux when we make that change?
the K1, the torque constant, K1 is flux multiplied by that armature constant. So the armature constant was G over 60 multiplied by phi over A. That is the armature constant. And if you multiply the flux, that gives you the K1. So, but in this problem, current problem 3, I mean today that we are discussing, those things are not given. Now total number of conductors, in the parallel paths, those are not given. So from the equation, you have to find out the torque constant. Like you said that equation, that back voltage is K1 multiplied by omega. That's the right equation. So from that equation, find out the K1 value. So I'm talking about the first part.
Okay, thank you.
Yeah, I think now it is fine to you.
Yeah, that's helpful.
Yeah. Alajmi, so you open the class notes for the last class, last or the previous class, especially the last class, and see those numerical problems. There are required equation, that process, everything, and then use those concepts to solve these problems.
Okay, Professor.
Okay. So today we are practicing, so you feel free to open the previous class notes, anything. This is not the exam, just practice. Joel, are you getting the results?
I'm working on the first one.
Oh, okay. So please take your time. As I said, you feel free to open the class notes, especially the last class. And I think 3-4 problems were solved. You look those and then use the required equation to solve these problems. And then answers are written in green color, so you can match with the answers that you are doing correctly. Sam, are you getting properly?
Yes, sir. I got the torque constant for 3, and I'm working on the power output now.
Okay, great. Yeah. So anybody, in case you get different result than me, then let me know. I will check my calculator again. Yeah.
Dr. Lee.
Yes.
So I'm trying number 4. And so
Is it
Wait.
number 3? Are you talking number 3?
no, number 4.
Oh, okay. Oh, no, is number 3 fine? The
Yeah,
both.
I got it. Number 3 is good. It's
Oh,
gone.
okay, great. Number 4.
Um,
Great. That's great.
yeah, I wanted to ask about so the formula from yesterday for universal motors, or last class rather.
Mhm.
We have EAC over EDC is equal to omega AC over omega DC.
Mhm.
So for EAC, should we be using the peak value of 120 volt?
120, right. That is, yeah.
Okay.
That is the RMS value actually.
Yeah. Oh, so EAC should be the RMS value?
Yes. ESC should be RMS.
Okay. Okay.
Yeah. So in the original equation, like ESC over EDC, omega DC, that is the RMS value.
Okay. All right. Thank you.
Okay.
Dr. Ali, for number 3, the second part, power output. So I'm using the equation that we went over last time, where I have the power is equal to EB times IA minus the power loss.
Yeah.
So I'm.
Yeah, that's right.
That's right. Okay, so I'm plugging in for IA, and then I'm using the other equation, but I'm not sure what to put for VT on that. I think I have everything else.
So you need the new value of IA and new value of back voltage. So you know from the first part. So did you calculate the torque constant first part?
Yes, sir.
Okay, and you got that 0.28, right? Yeah.
Yes, sir.
Now using that torque constant, you have to find out the new value of back voltage EB. Using that same torque constant number, you have to find out the new value of EB. And that new EB will go into your equation that you just said. Output power is EBIA minus the loss. So that EB will be the new EB, not the previous parts EB. And there will be the new current. IA will also be the new. But then you know IA, what is the IA? IA is VT minus CV over RA.
Oh, okay. All right, I got it. All right, let me take a few minutes.
Yeah, no, sure, everybody, but please take time. Everybody look carefully, and then there will be a new IA. As you can see, the source has been changed. Now the source voltage is 50 volt. Yeah. For the first part, the source voltage was 60 volt, but the now source has been changed 50 volt. And even the motor rotation has been changed now 1550. That's why you should be getting new back voltage and new armature current. So, okay, please keep trying.
So is the new EB for number 3, part B? I got 45.45.
Yeah, like 45.49, but it looks like you are right. Yeah.
Okay, all right. And then I got a number that's very close to the horsepower.
Yeah, and then what is your new armature current?
Well, I didn't solve for that separately. I plugged in the variables first, so I don't know exactly.
Okay, so please calculate the new armature current as well, using that new back voltage that you said just now. Yeah. You need the new armature current as well, because output power equation, EVIA, then minus the loss. So that.
All right, I got 3.5 for the current.
Yeah, approximately, like my calculation shows 3.47, but it looks like you're fine, right? So now use in that output power equation that new EB and that new IA that you said, and then minus the power loss, and then you convert into horsepower by dividing 746. Then you see that you are getting that result nearby. I think it's a small value, 0.097 horsepower. Is this fine? Did you get the same result?
Yes, sir, I got it.
Yeah, okay. Okay. Hello, Chris. Chris Butler, are you trying? So, Alexandria, are you done with number 3?
Yes, on number 4 now.
Oh, okay, great.
Hey, Dr. Charlie. I got part A to number 4. I'm working on part B.
Oh, okay. So
Um,
did you get the same result, torque value?
Yes, I got 0.289.
Okay.
I'm looking at part B, and so I'm guessing we need to use the torque times the power. But
yeah. I mean, torque equal to power over omega,
oh, my bad. Yeah, power over torque. I didn't say torque times power. I don't know why I said that. Anywho, I'm trying to find the power for DC. Am I able to just use I squared times 22?
No.
Or,
I mean, in case of both AC and DC, that mechanical power is back voltage multiplied by the current.
yeah, I haven't found the voltage at the motor. I haven't found the actual back voltage.
Okay. So therefore, what you need to do in case of the DC, you need to find out the back voltage, EDC.
Let me see how to do that.
Yeah. So see all the required equation. I think last class we did on similar problem, very similar problems. But I think in last class I asked the torque and speed for the in case of the AC voltage. Today, I think I am asking in case of DC. So therefore, look last
Well,
the similar problems.
so we have the current going into it as 0.5 amps. That's what it says the current is.
Yeah. Right.
Can we just use that 22 ohm resistance value,
Yeah,
or
of course, the same.
so? Okay, so that 22 ohms is like the armature resistance then.
Yeah, exactly.
Okay, so then yeah, that's fine. Easy.
Yeah. That reactance basically that series field reactance.
Okay. All right. Thank you.
Okay, please keep trying. Yeah.
So I got something different. So
The speed.
yeah, I got like 2 times what that is.
Okay.
I found the back voltage to be 109.
Yeah, that's right.
Okay, so I use 109 equals K1 omega, and we have K1 as 0.289. So I did 109 divided by 0.289 to get omega.
So you see, because this is that universal motor. So you mentioned that equation EAC over EDC equal to omega AC over omega DC. Use that equation.
Use that instead.
Yeah. Use that equation. EAC over EDC equal to omega AC over omega DC.
Okay, yeah, I can do that too.
Yeah, and then you plug in all those numbers.
Yeah, when I do it that way, I get 188.45.
Yeah.
So is there a reason why it doesn't work doing K1 omega?
So this is that universal motor case.
Oh, I'm also, I use straight torque value. That's why I I acted like K1 was yeah.
Universal motor in this case. It is not the permanent magnet motor.
Yeah.
Yeah.
But I also use the torque as if it was just the torque constant instead, and that was not good.
Yeah, so therefore,
Yeah.
therefore, the first step should be for number 4. You once you got the omega DC value, and then now you write down the torque equation, and then torque is power over omega.
Yeah.
Therefore, E DC multiplied by I DC, that should be your power, and then over omega DC. I mean, in the problem, in the question, although first I am asking calculate the developed torque and speed of the motor, this does not necessarily mean that first you have to calculate the torque. Yeah. First, you might calculate speed and then use that speed to calculate the torque.
Yeah, okay.
Yeah, yeah.
Which if you, well, you just said that it's not permanent magnets, so the torque constant isn't actually there, I guess. There's no real
Yeah,
torque
yeah.
constant for these.
Yeah.
Okay.
So,
Then yeah, then I've got the answer for 4, then I'm good.
yeah. And then there is last problem, number 5 for today. That's all. So far, is everybody done with at least number 1 and number 2? Is everybody done? Or in case anybody have any issue, then please let me know. I will help you. And then if you are done number 1 and 2, then start number 3. And if anything, if you are done, then you always try the next one. And that's why the answers are written. You match with the answers and keep trying.
For number 4, is the omega DC equal to 188.45?
Yeah, that's right.
Oh, okay, I got you.
Yeah.
Okay, yeah, thank you.
Yeah, sure. So that is, that in green color I have written part B. That is the answer.
Okay, yeah, all right. My bad.
No, you're fully fine. Let me write down that this is the speed. Speed. Yeah. Now I wrote speed equal to 188.45 radian per second. Okay, and then once you get that speed, use that speed information to calculate the torque. That was I was telling to Tyler that that first it is developed torque. Although question says calculate the developed torque speed, this does not mean that at first you have to calculate the torque. Yeah. I mean, it is not that sequence. First you can calculate speed and then use that speed information to calculate torque.
Okay, I also got the correct torque. Thank you.
Okay, great. Then those who are done like until 4, then you keep trying number 5. And that's all for today. Only there are 5 problems.
So the reactance for number 4 was unused, right?
For number 4, what
We
is
did not
unused?
use
You said?
reactance.
What
Uh,
is
y- yeah, the reactance was unused because we were using DC and inductance is a short, right?
Oh, yeah. So you are talking about the reactance value, right? 100 ohm?
Yes.
Yeah. So for number 4, you need to calculate the back voltage for DC. And to calculate the back voltage, because that is DC, so that inductance will be short circuited. So only you have to use 22 ohm resistance value. And the armature current is that same 0.5 ampere. Yeah. And the back voltage for AC source is given. You see the third line, when the motor is supplied by AC power, its back voltage is 98 volt. Yeah. That is in case of the AC. So you have to find out the EDC. This means back voltage in case of DC.
So for number 5, I'm trying to find the back voltage currently. What I was trying to do was do the terminal voltage minus IA times 20 plus J100.
Yeah. So you are right. And there will be like phase angle. So you don't need to do that. Just find out the magnitude.
Yeah.
So for 20 plus J100, for that one, you just take the magnitude portion and then multiply with current. That's why I said just calculate the magnitude of the back voltage.
Okay. Let me see if that changes my answer then.
Yeah.
Okay, yeah, that changes things a lot. That gave me the correct back voltage.
Yeah. So is this number correct? 69?
Yeah, that's what I ended up getting to.
Okay. I think I approximated approximately 69 volt.
It's honestly it's almost exactly right because the magnitude you get for that is almost 102 exactly. It's 101.98, so it's not that harsh of an approximation. It's very close.
Okay. Yeah. So, yeah. Right. Yes. Yeah. Now I noticed that. I also like got that. Yes. Pure rounded number 69. Right. Yeah.
Okay. So I'm not getting the same answer. Did you do? You basically have 120 minus 0.5 times 20 plus J100.
Right. That's right.
Okay. And then you end up with 120 minus 10 minus J50.
Yeah, he said take the magnitude of the 20 plus J100 first.
Okay. Take the magnitude first. Okay.
Yeah, it changes things a lot.
Okay.
Yeah.
All right. I'll do that.
You just take the magnitude.
Okay. I was waiting till the end to take the magnitude, but I'll do it first.
Yeah, I was gonna wait to the end too.
Right. And then use that magnitude only. Don't include the angle. Yeah. Like 20 plus J100, the magnitude should be root over 20 square plus 100 square. Or in your calculator, convert that on into polar form, but take the magnitude only. Yeah. Or use the root over 20 square plus 100 square, the same thing.
So are we going to be considering that angle that we discarded for the power factor?
Yeah. So what is that last one? The power factor. So Tyler, did you calculate that power factor?
I haven't yet, no, but we have the angle of 78.69. So you would just cosine inverse that, I guess.
Okay, yeah. Then
All right. Yeah, I got 0.196.
Yeah. I approximated that one. Simply I wrote 0.2. But I think you said 0.19 something, right? Yeah.
Yes, sir.
Yeah. I just approximated 0.2 just to show a good number, but I think you're right. Or without the angle, if you use that impedance triangle, you remember impedance triangle, x-axis base is r, and then vertical axis is x, and then hypotenuse is g. G is root over r square plus x square. So, or in other words, power factor cosine theta is r over g, resistance over magnitude of impedance. Then you should be getting the same result. I mean, what you said with the angle, that's right, absolutely right. But also without the angle, what you can do, cos theta is r over g, base over hypotenuse. Do you understand what I'm saying? If you draw the impedance triangle like R, X, and J relationship, x-axis is your base is your R, then perpendicular is your X reactance, and then hypotenuse is the impedance J. But then J magnitude is root over R square plus X square, which is root over 20 square plus 100 square. That is used to calculate the magnitude of the impedance, to calculate EB. Then cos theta is R over J. Is this fine?
So yeah, doing it both ways. I've got
yeah.
I got the same number as Sam for 0.196 if you just do cosine of 78.69, and then 0.2 if you do r over j.
Yeah. R over that is the basic definition, And essentially what you said, if you consider the angle with the G, that is the power factor angle. Like you are calculating the angle, like G is magnitude together with some angle, and then cosine of that angle, that is the power factor.
Yeah.
And that is the same meaning as saying cos theta is R over G. That's why I'm referring to that impedance. If you draw, and then you can relate it both ways. It is the same thing. Yes, similarly, when it is power triangle, when the power values are available, your base is active power or real power, then reactive power, vertical axis or perpendicular, and then apparent power, hypotenuse. S is root over v square plus q square, that magnitude. And then cosine theta is p over s, apparent power. Or in other words, p is s cosine theta. Therefore, with the complex power, the angle you will be getting with the complex power. And then if you take the cosine of that complex power, it is the power factor, the same thing. Similarly, like what you said, you are absolutely right. The cosine theta of the angle that you are getting with G impedance. So therefore, I mean, both are analogous. This impedance triangle or that power triangle, the same meaning. So is everybody done with number 3? Everybody?
Yes, I'm done. I'm on number 5 right now.
Oh, okay. Oh, great.
I'm on 3B still.
Oh, 3B. Okay.
Yeah, I'm on number 5. I'm almost done with 5.
Okay, yeah. So everybody, please keep trying. Yeah. Then I believe we all will be doing well in the upcoming third midterm exam. And soon, I have not graded your midterm exam too. I mean, soon I'll be doing. Hopefully by this weekend I can complete. Once I am done, I will notify you. You can see your grade. And also, I'll be discussing some of the answers for the exam. And also, I think I did not let you know the grade for homework 3 and 4. I will do that as well, plus the class quiz that you did in last class. So for this course, we are almost like 95%, and only one chapter is remaining, which is like chapter 10 from the book, Transients in Electric Machines, that I will be covering in next 2 classes. Then we will be done. So you can say we are done about 90 to 95% of the syllabus. So only last chapter is remaining, and few of the motors that I will be talking in next class at the beginning.
Dr. Ali, do we need to stay if we finish number 5?
And no, so those who are done, you can leave. Yeah, because there is nothing after that. So you can leave.
Okay, thank you. See you next week.
Okay, see you. Bye. Hello, Chris Butler. Are you trying? Josue, are you getting the results? Alexandria, are you done with number 5?
I'm almost done.
Okay, sure. Okay, take time.
Dr. Ali, I just finished number 5. I got the same answers.
Oh, okay, great, Nathan.
All right. I'll see you next class. Thank you.
Okay, see you.
just finished number 5 and got the same answer.
Oh, okay, great. So like
And
for the EB equation, it was like VT minus I multiplied by RA plus JXA, right? Yeah.
yes.
Yeah, okay, great. And then you took the magnitude for RA plus JX, I mean 20 plus J100, right? Yeah.
Yes.
Okay, great. And then how did you calculate the power factor?
I went through the last slides after I'd gotten the magnitude and stuff.
Okay. So therefore, I mean, two ways you could do that. Impedance 20 plus J100, you can calculate its magnitude, and you may see there is an angle with that. So cosine theta, cosine of that angle. This is one way. The other way is that power factor cosine theta is R over J, resistance over the magnitude of impedance. So this means 20 over root over 20 square plus 100 square. So then still you should be getting the same result. So either
You said, sorry, I just wanted to write that down. You said, what was the second way I could have done it?
second thing I told that if you see a impedance triangle like x-axis R, then y-axis is x, and then hypotenuse is G. G is root over R square plus x square.
Oh,
So
yes. Okay.
yeah. So cosine theta is base over hypotenuse. So R over G. G is the magnitude of impedance. So in this case, resistance value is 20. So 20 over what is the magnitude of impedance, which is root over 20 square plus 100 square. So then you should be getting the same result, 0.19 something. So approximately I wrote 0.2, or that you did that directly when you are calculating the impedance, its magnitude together with the angle. So then cosine of that angle, that is the same meaning.
Thank you.
Yeah. So just remember this basic definition. I mean, the second thing as well, that cos theta is R over G. G is the magnitude of the impedance. So this type of even simple questions are being asked in the FE exam. Like I have noticed some of the sample questions from the previous years. So these will really help you all to do well in the FE exam. Okay, so with that, if you are done, and then you can leave if you like. Yeah.
And I also saw your email about the lab.
I think I replied to you. Yeah.
Yes. Do I need to email the TA or?
No. I already verified with him.
Okay. Thank you so much.
Yeah. That's why I was late in replying to you. I saw your email when you sent last evening. I saw, but then I asked him.
Okay, good.
That Gold will be doing that, and then he made me late reply. This morning he replied. That's why I'm late. Yeah.
Okay, thank you so much. Have a good day.
Yeah. Same to you. Yeah. Same to you. Okay. Bye. So is everybody trying? So are you all done? Number 3, 4, or which one are you trying? So if you have any questions, anything, clarification. So Patrick, are you still trying?
Yeah. Only thing confusing me now is number 5.
Okay.
Um.
So number 5, you are asked to calculate the magnitude of back voltage. So back voltage is VT minus IA multiplied by RA plus JX. You see, because this is AC universal motor. So now you have to take into account the reactance as well. So therefore impedance is, our resistance value is 20. So 20 plus J100. So 20 plus J100 is your impedance. So you first you write down the equation for back voltage EB is terminal voltage VT minus IA multiplied by the impedance. That impedance is RA plus JX that I said. And you take only the magnitude portion of the impedance. Do you get it?
Oh, yeah. I can't believe I forgot about that.
Yeah. Then you
Thank-
should, 69 volt. And then to calculate the power factor, cosine theta is R over J, resistance over magnitude of the impedance. That is the definition of power factor cosine theta.
Okay, thank you.
Okay. So JC, are you done?
Yeah, just finishing up number 5.
Okay, great. Joel, where are you now?
I keep getting 3B wrong. I've come up with 0.105 and
Okay.
0.095.
So 3B, what you did, first of all, for 3B, output power is back voltage multiplied by the current minus the loss. Did you subtract the loss? 85?
Okay. Yeah, I've got the no load rotational loss as 92.672 watts.
No, you don't need to calculate the no load rotational loss because
Oh,
we are not asking for this problem. So you see the no loss is given in the last line of the problem. Assume the rotational losses of the motor 85 watt.
oh, okay.
So you have to subtract this 85. So, I mean, last class we were discussing, there was another question, no load rotational loss, but today we are not asking that on. Yeah. So the loss value is given, which is 85 watt. So you have to subtract that on 85. But your EB, back voltage and armature current, they should be the new, not for the value of the previous part.
Right.
Yeah. So you got the torque constant correct, right? 0.28 approximately. Is that right?
Yes.
Okay. Then using that torque constant, you calculate the new value of back voltage, EB. Like EB is K1 multiplied by omega.
I think maybe my rounding is, I did 0.279 instead of 0.28. Maybe that's what's making it be off.
Okay. So what's your new back voltage EB? Like it
I
should,
had 45.3 is my new back voltage.
okay. And then what's the new current?
3.615.
Yeah. I mean, you are nearby. I think because your K1 value little bit deviated than 0.28. That's why I think, but those looks good.
Okay.
And
Okay.
then you multiplied EBIA and then subtract that loss that I said, which
Yep.
yeah.
85. Okay.
And then you divided that result by 746 to convert into horsepower.
Right.
Yeah. Then you should be getting nearby that on 0.097 nearby.
Okay. All right. Got that one.
Okay. Great.
Looks good. I'll see you Tuesday, Ali.
Yeah. So JC, so are you done with number 5? Oh, I think he left. Yeah. Josue, are you still trying? Chris, are you on the line or you are not on the line? So Patrick, did you get the same back voltage and power factor?
I get the same back voltage. I'm still working on power factor.
Okay. So as I said, cost. So what you can do, you can calculate that impedance like 20 plus J100, and you convert into polar form, and the angle you will be getting with the J, take cosine of that angle. That is your power factor answer. That is one way of that is one way of doing that. The other way is that, as I said, power factor cosine theta is R over J. R is the resistance and then J is the magnitude of impedance. So therefore, both ways should be getting the same result.
Okay, I've got them.
Yeah. So therefore, I approximated. I mean, it is not like fully 0.2, 0.196 something. I just approximated to show a good number. So I showed 0.2. You might leave 0.196, whatever you are getting.
It's like a 0.19 something something something.
Yeah. That's why I approximated 0.2.
All right.
Okay.
Thank you.
Okay. Thanks. See you.
See you.
So Joel, so are you trying number 4?
Yes, I'm just setting it up right now.
Yeah. So you see, as a hint, you should use that equation like EAC over EDC equal to omega AC over omega DC. That universal motor equation that relates back voltage and speed.
Okay, I see that now. Yeah.
Yeah. So EAC over EDC equal to omega AC over omega DC. We did on similar problem last class, but in last class, I think the question was find out the torque and speed when it was connected to AC source. Today, I am asking when a motor is connected to DC voltage source. That's the question.
Okay.
Yeah.
Thanks.
So by using that equation, first you have to find out what is the DC speed of the motor in case of DC, omega DC. And once you get that, then the torque equation is power over omega, but power is EDC multiplied by IDC. Now you have to calculate what is the EDC, that VT minus IRA, using that equation.
Okay.
Yeah.
Okay, I see that. Yeah.
Yeah. Right here. You see the AC back voltage is given 90 volt, but you need to calculate EDC, which is VT minus IRA. Yeah. And I value is the same, the very first line 0.5 ampere, and RA value is 22 ohm. So you don't need to use the 100 because that is the reactance. Because you are calculating back voltage for DC, EDC, so inductor will be short circuited. So you don't need to use the reactance, only the resistance 22 ohm.
Okay.
Yeah. Then you should be getting that torque value and the speed value same.
Okay, so okay, and then I'll convert the RPMs into radians.
Right.
Okay.
Yeah. Okay. So did you get 188.45 approximately radian per second?
Yeah, I got 188.47
Yeah,
for Mega
that's
DC.
fine. That's fully fine. And then to calculate the torque, you just now note down the torque is power over omega. So in this case, the power is DC power. So EDC multiplied by IDC. I mean, back voltage of DC multiplied by back voltage, sorry, the current DC over omega DC. That omega DC that just now you calculated 188.47. So now you have to, the IDC is the same, which is the very first line, you see, 0.5 ampere. That is the IDC.
Okay.
But you need to calculate the EDC. That EDC is, you note down in your note, EDC is VT minus IARA,
Okay, yeah, I got that one.
109 watt.
Yep.
Yeah, so therefore 109 multiplied by current 0.5 divided by 188.45. So you do, then you should be getting approximately 0.289 Newton meter.
Yep, that's what I got.
Right. And then read number 5. I'm giving you the hints, so you can do number 5.
Okay.
So in this case, this is the AC universal motor. This means this is powered by the AC. Terminal voltage is given on 20, armature current is 0.5, and operating that RPM. If the resistance and reactance of the motor is 20 ohm, 100 ohm respectively, then calculate the magnitude of the back voltage and power factor. Now, first of all, that back voltage, you write down that back voltage EV is VT minus, in this case, IA multiplied by the impedance. Impedance is RA plus JX. Because it is AC motor, AC universal. So now you have to take into account the reactance as well.
Okay, I see.
So therefore, this means VT minus IA multiplied by RA plus JX. In other words, impedance. And IA is your same, which is 0.5. VT is 120 volt, that is fine. And
Okay.
then you calculate the magnitude of the impedance. You don't need to consider the angle. Only you take the magnitude. I mean 20 plus J100. From there you take the magnitude portion of the impedance. And then if you do that, then you should be getting 69 watt.
Okay.
Okay. And then for the last part, power factor part, now once you are calculating the impedance like 20 plus J100, I mean, you use the magnitude to calculate EB, that's fine. But if you keep its angle, phase angle, and then take the cosine of that angle, that is your power factor.
Right. Okay, so cosine of that angle.
That angle, that is. So this is one way of doing that. The other way of doing power factor, basic definition from impedance triangle, cosine theta is resistance over impedance, R over G, magnitude of G. So this means power factor is R over like 20 over root over 20 square plus 100 square, the magnitude of the impedance. That also you will be getting like 0.196 something. So I rounded it 0.2.
Okay.
Okay, is this fine? Yeah.
Yep, I got that all written down, so I think I can get it.
Yeah, okay. So thank you. So and then once again, you look everything at your free time. So then everything will be fine, clear.
Yeah, thanks. Thanks for your help.
Okay, so with that, I think already we are over time. So I am stop sharing. I mean, already these slides are uploaded on EcoShare.
Sounds good.
Yeah, I will stop sharing.